first is going to be PGL2 F4 exceptional theta correspondence. And the second topic, we'll go through Knopp and Schalke's construction of the dual group of a spherical variety. And I should mention, I could mention that this first topic is joint work with Gordon Savage. All right. So let me just quickly remark on the connection between these two topics. So from the exceptional theta correspondence, this PGL2 F4 exceptional theta correspondence, so I'm going to describe the connection. So this PGL2 F4 theta correspondence, this gives us a way of characterizing the spin 9 distinguished representations of F4. And so in particular, this puts us in the realm of the relative Langlands program, specifically dealing with the rank 1 exceptional spherical variety of F4 mod spin 9. And let me just mention what the characterization is. These spin 9 distinguished F4 representations, these arise from the exceptional theta correspondence as exactly the generic representations of PGL2. We characterize the spin 9 distinguished F4 representations as the lifts of the generic representations. Okay, so let me just quickly outline what I'm going to do today. And feel free to interrupt me at any point for questions. All right, so I'll move on to page 2. So what are we going to do today? So the first thing that I want to do is I want to just do a basic introduction to some of the exceptional algebraic structures that are going to appear. And I'll do sort of a broad overview. Not everything will be strictly necessary for this PGL2 F4 exceptional theta correspondence, but I think it's good just to sort of get your bearings. And so in particular, the first thing that I'll talk about today is just some basic overview, maybe basic properties of composition algebras. These sort of form the building blocks for a lot of the exceptional groups, or at least some of the building blocks for the exceptional groups. And these tend to be a little bit more accessible. Let's see. And then one of the things that I'd like to prove today is that, okay, so one example of a composition algebra are octonion algebras. And I'll prove that the automorphism group of the octonions is a group of type G2. And so we'll see the exceptional groups emerging as groups of automorphisms for some of these exceptional algebras. Okay. All right, and then lastly, I'll just go through several constructions that will be related specifically to the PGL2 cross F4 exceptional theta correspondence. So, All right. Okay, so I'll begin with composition algebras. Any questions before I get started? All right. I have to figure out how to better navigate the Zoom whiteboard, though. All right, composition algebra. All right, so let me just begin with the definition. Actually, first, K is just going to be a field. Let's assume that the characteristic of K is not equal to 2. All right. So let's let C be a finite dimensional K algebra with units. And we're not going to assume that this is associative. And let's assume that we also have a quadratic form on C, a non-degenerate quadratic form. All right, so right now we have these two structures, a finite dimensional K algebra with unit, not necessarily associative, and a non-degenerate quadratic form. And a composition algebra is going to be coming from the interaction between these two structures. And so we'll say that the pair CQ is a composition algebra over K. If we have the following identity which holds. The quadratic form on the product x times y is equal to quadratic form on x times the quadratic form on y for all x and y in C. All right, let me begin by just giving, not scroll too much. All right, so let's just go through several examples. And in some sense, these will be all of the examples, all of the possibilities. All right. Okay, so certainly we can take C to be K and our quadratic form to be x goes to x squared. So this is in fact the only dimension 1 composition algebra. All right, there's some more examples in dimension 2. We can take 2 copies of K, and our quadratic form can just be coming from multiplying those 2 values together. We can take a quadratic field extension. And then our quadratic form is going to be the norm form. And in fact, that's all of the 2-dimensional examples. And now here's a 4-dimensional example. We'll take 2 by 2 matrices, entries in K, and we can take the determinant to give a quadratic form. All right, so this is a four-dimensional example. This is an example of a quaternion algebra. And in fact, all quaternion algebras are composition algebras. Let me not give a definition of quaternion algebras right now. For our purposes, they will be just four-dimensional composition algebras. But if you're familiar with some other definitions of quaternion algebras, they will give examples of these composition algebras. Okay, and then finally, there are the octonion algebras. Ready? Okay. All right, so as we continue, we'll find that these are in fact sort of all of the examples when you define quaternion algebras as four-dimensional composition algebras, and when you define octonion algebras to be eight-dimensional composition algebras. This list exhausts everything. So in particular, the dimensions are severely restricted. All right, and let me just comment right now that all of the examples except for the octonions are associative. So the octonions are non-associative. Okay, so the next thing I'd like to do is just describe some basic properties of composition algebras. Okay, so first off, just a little notation. So we have this quadratic form, and attached to the quadratic form, there is a bilinear form. Maybe sometimes I'll call this B sub Q. And by definition, this is just the quadratic form at x plus y minus the quadratic form at x minus the quadratic form at y. Okay. We can define a trace so actually, let me say throughout x, y, and maybe z, these will just be coming from our composition algebra C. We'll define a trace as just being the pairing of x with the identity, the unit in C. And so then we can also introduce the trace zero elements. Now, this is a hyperplane inside of a quadratic space, and so we can look at the reflection which fixes C0. Oh, and let me also say that 1 is not in this space. So we can look at the reflection which fixes this hyperplane, this trace zero hyperplane, and which flips the unit element. And then we can negate that to introduce sort of the involution on the composition algebra. So there's this involution. Let's take this. Okay, so let's let R sub 1 goes from C to C, can be the reflection. This is the trace zero elements and sends 1 to -1. Okay, and now we can define some involution. It's just going to be minus R1 of X. And we'll occasionally just write bar to mean this involution applied to X. Okay, so it's not clear that it's an involution at this point. That won't prove that, but let me state some of the properties in just a moment. Okay. So I want to list a few important identities and properties of these structures that I've just introduced. All right, and so throughout, we will have every X, Y, and Z in the composition algebra. We have the following. Do this as a list. Okay, so the first thing which is very important is that these elements in a composition algebra, they satisfy a minimal polynomial, a quadratic minimal. Okay, so a quadratic characteristic polynomial. So in particular, x squared minus the trace of x times x plus the quadratic form. This is equal to 0. I'll prove this in a moment. And this is a really important identity for the structure of these composition algebras. All right, now we introduced this involution, and it turns out that the trace and the quadratic form can be written in terms of the involution. So the quadratic form, this is just going to be x times the involution of x, and the order doesn't matter. And the trace of any element will be x plus the involution. All right, now I've been saying this, but I haven't actually justified it, and I don't think I will. But this bar operator that was introduced, this is actually an anti-involution. This is an anti-involution on the composition algebra. All right, I mentioned that composition algebras can possibly be non-associative, but they can't be completely non-associative. There are some strong associativity properties that still hold. And so in fact, a composition algebra is what's known as alternative. And this means the following, so that for every x and y in C, let me just write it, it doesn't make much sense. Let me write something on the side here. Okay, so when we study non-commutative algebras, we introduce the commutator, which sort of measures the failure of commutativity. And for non-associative algebras, there's a similar type of construction. There's the associator. And so we'll write sort of squiggly brackets, x, y, z. Just by definition, this is going to be x times y times z minus x times y times z. All right, and to be alternative, This just means that x, y equals x, y equals 0 for all x and y. All right. Okay, so again, the composition algebra may not be associative, but sort of associativity holds at the level of the trace. So if you have x times y times z and you take the trace, that's the same as x times z times y times z. Okay. All right, and lastly, what I want to mention is there are these things called Mufang identities. So again, these are some identities that sort of stand in for the failure of associativity. So again, these algebras, some of them can be non-associative, these octonion algebras can be non-associative, but you have some identities that sort of play the role of associativity. So I'm not going to say very much about the Mufang identities, won't even write them down. I'll mention where they come up from time to time. All right. Okay, so this is just a list of a bunch of properties. I want to prove the first one because it sort of illustrates some nice techniques when you want to investigate these algebras. And then from that first one, we'll be able to very easily get the second and the third properties as well. Okay, so let me prove the characteristic polynomial identity. Maybe I'll stop any questions before I continue. Yeah. Sorry, could you speak up?
So the denominator kind of trace or something based on the choice of the reflection.
We are always taking the reflection which fixes the trace 0. Okay, sorry. So let me say again. Yes, because it's all based, because we have an algebra, we have with units, that's a distinguished vector. And so the trace 0 space is basically the vectors which are orthogonal to the identity element. So that's canonical. And then the reflection is the one which fixes the trace 0 space and flips the identity. So that's also canonical. So there have been no choices in that construction so far. Does that answer your question?
So that
It's canonical. We haven't had to choose anything. It's all coming directly from the given structure of the composition algebra. All right. Okay, so we don't have a lot to work with to prove an identity like this. We have finite dimensional algebra, we have this quadratic structure on top of it, and the only interaction is coming from this multiplicativity of the quadratic form. So this is the only thing that we have to use. And so let's just see what that gives us. So here's sort of an aside. The only thing we know are the following two facts. We have this non-degenerate quadratic form. I'll write this as the bilinear form. Okay. And we have the multiplicativity of the quadratic form. So we have to combine these two in some way. That's all we have to work with at this point. All right. Okay, so the first thing that we'll do is let's just take a look at item 2, and let's rewrite this in terms of the bilinear form, but we'll do this sort of in steps. So if I take the bilinear form and I multiply this by the quadratic form, well, I can expand the bilinear form in terms of the quadratic form. And I can just regroup and use the multiplicativity. Maybe I won't write everything out. But what happens is this z can sort of get absorbed inside. So now we get the bilinear form of x times z, comma, y times z. Okay. All right. All right, and so we can actually do this again, replacing the quadratic form by another bilinear form. What am I gonna write? ZW. Okay. All right, so now we can sort of do this twice. There's some algebra, let me not bother with that. And what pops out on the other side is the following expression. Okay. All right. Okay, and so now the thing that we want to think about is we want to use the non-degeneracy. And in order to use the non-degeneracy, we have to get a bilinear form with an arbitrary thing on one side and then some other expression on the other side that doesn't involve that. And if you just stare at this expression for a little bit, you'll find that you can achieve this by making the following substitution or specialization. So if you specialize to z is equal to x and w is equal to 1, this gives us the following. It gives us exactly so again, I'm skipping a bunch of algebra. So again, this is exactly that characteristic polynomial. And so by the non-degeneracy, we get that this is 0. All right. Okay, so let me make one remark and then I'll derive the two previous claims. So I claim that I can also show that how to rewrite the quadratic form and the trace form in terms of this involution. All right. Okay, so if X is in the composition algebra, but not a multiple of the identity, then the characteristic, and this is like the unique, then this is unique. Is the unique monic quadratic polynomial killing X. So in particular, we can actually construct one using the involution. I can take X minus X times X minus X bar. And if you write out what you get, and you can also do this in the other order. So this implies that the trace is the sum and the quadratic form is the product. All right.
How do you do that for the second part?
You're asking about this one here?
I mean, x squared minus x plus x complete. Yes, the one you have.
Yeah, sorry, and your question is?
I don't know why this polynomial is in K. The coefficient of this polynomial is K.
Oh, yes, I see. Okay, so let's see. So these are, let's see.
X. Yeah, the x squared, the x on the x squared is the integral.
So the involution is just a linear transformation of C. And it's fixed space. So the reflection fixed space is the trace zero elements, and then it flips the unit. And then we're composing with -1. Okay, and so that means that the only thing that's going to be fixed will be the line through the identity. That's okay? Okay, great. Okay, and so so x plus x bar, this will be in K because it's fixed under the involution. Okay. Okay, but now, yes, maybe I do need to be a little careful about this last point. Because it's an anti-involution, it's going to flip it. Let me come back to that. Remind me at the end, and I'll think about it. There should be a way to fix that. Okay. Okay. All right. Okay, so we've described some basic properties of composition algebras. Very slowly. All right. But now I want to describe the most important construction for composition algebras. This is known as doubling. All right. So the input, this is just going to be some composition algebra. And non-zero element of the field. Okay, and the output will be a K algebra. It's not always going to be a composition algebra. So let me just describe this K algebra. Okay, so first off, so I'll call this D, maybe I'll sometimes call this D of C comma lambda. Sometimes this is called I guess the lambda double of C. Okay, and as a K module, this is just 2 copies of C. All right, so what is the multiplication? So if I take 2 elements, let's say UV and XY, the multiplication will be UX plus lambda Y bar V, comma, YU plus VX bar. Yeah, okay. This has a unit, which is going to be 1, 0. And this also has an involution. So if I take UV and I apply this involution, it's going to be the involution in the first entry and then minus the second entry. Okay. Then we also have a quadratic form. This would be Q of U minus lambda Q of V. Okay. All right, so this is just some some construction of a new algebra out of a composition algebra. It's got a lot of nice structure, multiplication, involution, quadratic form. Okay. But at some sense, in some sense, you lose something at every step. If you start with some nice algebra and you apply this doubling method, you're going to lose a little bit in the process. And so let me just list a few facts about this doubling construction. Let me do it like this. All right. So I make it a little more space. Let me move this. All right, so D, this is 1. So D is associative and commutative. This happens if and only if C is associative and commutative. And the involution of C is just the identity. This happens, for example, let me put this over. This is going to only happen for that one-dimensional composition algebra. Okay, let's see. So now D is associative if and only if C is associative and commutative. All right, so you start with associative and commutative, you apply doubling, you lose the commutativity, but you retain associativity. And maybe I'll also point out that associative and commutative, this you will get for your quadratic composition algebras. All right, and then finally, E is alternative if and only if C is associative. All right. Okay, so what you can see from this is that if you start with if you start with the one-dimensional composition algebra, you can only double 3 times. Sorry, what I should say is you can only double 3 times and get a composition algebra. Yeah, and this is because composition algebras are alternative. Would anyone like to hear more detail, or is that okay? All right. And so now I'd like to state Hurwitz's theorem, which just gives a classification of the composition algebras. composition algebra CQ has dimension 1, 2, 4, or 8. And let's see. Furthermore, every composition algebra CQ can be constructed by repeated doubling. Starting with the one-dimensional composition algebra. All right, let me just say a word on the proof. I don't want to actually prove it, but I think at least one comment is in order. So basically the idea, I won't even write this down. So basically the idea is that you have this composition algebra, and what you can do is you can show that any sub-composition algebra is contained in its double. Okay, and so because these things are finite dimensional, you can only do that so many times. And so in particular, the composition algebra which you started with then eventually becomes the double of one of its subalgebras of half dimension. So that's basically the idea, and that's why doubling is really playing such an important role. It both constructs and exhausts all of these composition algebras. All right. Okay, so now I want to start to deal with properties that are a little bit more geometric and which are really going to play a role in the exceptional geometry. And so what we need to do is make a comparison between the exceptional geometries, which we're trying to understand, and sort of the classical geometries, which we understand quite a bit better. And so one of the most important theorems in understanding the classical geometry is Witt's theorem about extending isometries. And there is a related theorem for central simple algebras called the Skolem-Noether theorem. Let me state that one carefully, because that will directly apply to to quaternion algebras. But the thing that I want you to keep in mind is that both Skolem-Noether and Witt's theorem, these are all about extending, maybe let me just say it separately to avoid complicating the language. Witt's theorem is about taking isometric embeddings and then extending them to the whole space. So in particular, you're producing isometries on the full space from isometric embeddings on a subspace. And Skolem-Noether is about taking K-algebra embeddings on a subalgebra and extending them to automorphisms of the full algebra. So I'll state that one carefully. So these are all about extension problems. And in particular, they can be used to construct automorphisms or isometries. So let me state Skolem-Noether. Now, let me go on. I'll move on to page 3. It's a good place to break it up. All right. So I want to talk about Skolem-Noether. And Witt type results. And again, these are both about extending maps from substructures. Let me just state Skolem-Noether. So let A be a central simple algebra. Don't worry if you don't know what a central simple algebra is. 4-dimensional composition algebras will be central simple algebras, and that's the case that we're going to apply it to. So you can just think quaternion algebra if you're not familiar with central simple algebras. We want to let B contained in A be a simple subalgebra. Now, if we have some K algebra embedding of B into A, then there exists, let me see how I want to write this. We'll write it like this. And then, in fact, we can find an element A, a unit in A, such that this embedding arises via conjugation. Okay, so just to use slightly different language, rho extends to an inner automorphism of A. Okay, so it's in this sense that we have this, that this theorem is solving this extension problem. All right, now, as I had mentioned, quaternion algebras are central simple algebras. And so we get the following corollary. A four-dimensional composition algebra. This is just a quaternion algebra. In the group of K-algebra automorphisms, this is isomorphic to, let me call this PC cross. It's the projective group of units. All right, so one quaternion algebra is just the algebra of 2x2 matrices. And so then this is just saying that the automorphism group of 2x2 matrices is PGL2. All right. Can I scroll up, or does anyone need to see that any longer? Okay. All right, so here's a question, and this is what we will move to in the second part. Let's say that we have suppose that we have an octonion algebra. I guess I didn't write this down yet. So this is just a composition algebra with dimension 8. Okay. So what is the group of K-algebra automorphisms? Right, so in the second half of this first lecture, we'll show that this is in fact G2. Okay. All right, so, but how are we going to go about doing this? All right, so what we need to do is we need to sort of introduce the relevant geometric objects that are going to allow us to investigate this automorphism group. All right, and so here's an important concept. All right, so this is the notion of a special pair. So once again, we have these octonion algebras, they're composition algebras, so we know we can construct them via doubling. And so in particular, that means that a lot of the structure should be encoded in the sub-quaternion algebras. But we've also just seen that quaternion algebras have lots and lots of symmetries, a really big automorphism group. And so the notion of special pair is really just one that's going to rigidify the quaternion subalgebras. All right, so let me define this. All right, so we're going to fix two non-zero elements of the field. Right, then we have an ordered pair, AB, is a special lambda mu pair of a composition algebra CQ if we have the following. Okay, so first these will be trace zero elements. So when you pair them against the identity, you get zero. But then they'll also be orthogonal to each other. Okay. And then second, we want, I should write this, oh, no, that's fine, okay. All right, so this is an ordered pair, and so the quadratic form evaluated at A, this is going to be lambda, and the quadratic form evaluated at B, this will be mu. All right, let me make a few notes about this. Okay, so the first thing that's important is that this definition of special pair, this doesn't reference the algebra structure at all. It only represents, it only references the quadratic space. All right, and then the second thing I want to highlight is that if we, this is not, one has to do a little calculation for this, but if you look at the subalgebra, which is generated by a special pair, this will be a quaternion subalgebra, but it will also come sort of with a basis derived from the special pair. So the subalgebra generated by A and B inside of C is a quaternion subalgebra. And the elements 1, A, B, and A times B form a basis. Okay. All right, so the first important proposition, and this is going to go a long way towards showing that the automorphism group of an octonion algebra is G2, is that this automorphism group will act transitively on special pairs. So we'll have CQ, a composition algebra, and lambda mu, two non-zero elements of the field. If A, B, and let's call it A prime, B prime, are special lambda mu pairs, then there exists some phi, which is going to be an automorphism of C, such that phi of A is A prime and phi of B is B prime. Okay, all right. So let's let D be the quaternion subalgebra generated by A and B, and let's let D prime be the quaternion subalgebra generated by A prime and B prime. And let's consider the following linear transformation. Call this, let me call this psi. This is going to go from D to D prime. I just want this to be a linear transformation, and I have a basis for D, I have a basis for D prime. And I just want psi of 1 is going to go to 1, psi of A will go to A prime. Psi of B will go to B prime, and then psi of A, B, this will be psi of A prime, B prime. Okay. All right, now you can actually just check that in fact this is an algebra homomorphism. All right, so we have this K-algebra homomorphism, but in fact, this is also an isometric embedding because in the definition of special pair, we just have all of the sort of angle relations between the vectors, for lack of a better way to put that. So this is also an isometric embedding. So D via psi maps to D prime, but then D prime is a subalgebra of C. Okay. Okay, so now here we can use Witt's theorem to extend this. And let me call this, I'm going to call this overline side. That's not really great. I'll call this capital psi. All right. Okay, so we have this isometry, but we really want an algebra automorphism. So we need to modify capital psi a bit. Modify psi. All right. Okay, and so here, now we need to actually use some of the structure Okay, sorry, I should also maybe point out that this is sort of most interesting in the case of C being an octonion algebra. And so I'm kind of assuming that throughout, though this will also work for a quaternion subalgebra, a quaternion algebra. Okay. All right. So what I want to do is I want to take a quaternion subalgebra. I'll just take D. Okay. And then we're going to realize C as the double of D. Okay. So okay, so here's how this sort of works. So we have that the bilinear form on D is non-degenerate. And so C can be broken up as D plus D perp. B restricted to D is still non-degenerate. Okay. And now let me just choose some element C, which is in D perp, such that the quadratic form is non-trivial. Okay. All right, let me make a claim. Come back to this a little bit later. D D perp, this can be realized as just D times C. So let's assume this for now. The main point here is that this construction is realizing C as a capital C is being realized as a Q little c double. Okay, but let's assume this for now. And now we really just want to go and define a new map. We'll define, I'll call this capital Phi. This is going to go from C to C. All right, so everything in C can be written as a D, let's call this D1 plus D2C. Okay. We're just going to define this to be, what was I calling that? 1 second. Okay. So we're just going to take psi of D1 plus psi of D2. How do we define it on the C? The only thing we have to work with is this capital psi. And so now we can check that this capital B is a linear isomorphism. That's not so hard. And also a K algebra homomorphs. That's a little bit more involved, but let me just claim that. All right. Okay, and then by the definition of psi, this does take the special pair AB and maps it to A prime B prime. All right, so let me just say that this capital Phi is the desired map. Let me make one remark on the claim. Oh, no, I'm sorry. Flip things. So see if it begins. Okay, sorry. So I'll come back to the claim in a moment. I want to make a remark on showing that this is a K-algebra homomorphism. The reason why this is a little bit more tricky is because this is actually going to involve products of three terms, and since you don't have associativity, you got to do something. So let me make one remark on this point right here. Okay, so this is a little bit involved because of the failure of associativity. Okay, and so the point is that to really identify C as a double, you'll have to eventually use Mufang identities. So, oh, okay, and then finally for this point on the claim, so we can do the following. So we just want to show that D times C is perpendicular to D. So we're looking at terms of the form D prime C, D and D prime will be in D. Okay. All right, and then you can show the following identity. So this comes on the outside. Well, product is in D, D is perpendicular to C, and so you do get 0. I want to make one remark. About this equality. So this follows from the definition of the involution, but then also that identity we used in proving the characteristic polynomial equation. All right. Okay. All right. Okay. So this proposition is extremely important for what we're going to do in terms of analyzing the automorphism group of the octonion algebras. Any questions on this? Happy to spend more time here. This is sort of like one of the fundamental inputs for understanding the automorphism group. All right. Let's see. So Lei, was it difficult to take a break or something, or should I just keep going? Oh, okay. You guys need a break or just want to keep going? Okay, we'll keep going. Yeah, okay. Happily keep going. Let's see. All right. Okay, so all right, so now references. Yes, okay, so someone online is asking about references, and let me share some references. All right. So for a nice and elementary introduction to composition algebras, I would recommend Jacobson's Basic Algebra 1. For an elementary introduction to composition algebras. Let's see, and then there's also Springer-Veldkamp. don't remember the title of this book right now, but this is a Springer, there's a Springer text. Springer, the publisher. And in particular, this is where I'm taking the proof that I'm going to talk about, that the automorphisms of octonions is G2. I'm taking it from Springer-Veldkamp. See, and then also the Book of Involutions has a lot of useful information about all of these topics. So I think these three sources are quite good. Oh, one more. Aaron Pollock has a very nice set of notes about exceptional algebraic structures. All right, so these are some excellent references on this material and related material. All right. Okay. So now I'd like to turn to the proof that the automorphism group of the octonions is isomorphic to G2. And so, all right, let me move on to a new page. All right, so here I'm following the presentation in Springerville. All right. Okay. So at this point, I'm going to assume that K is algebraically closed just for simplicity. One can describe rational structures, but I don't want to do that. And as before, we're assuming that the characteristic is not 2. Okay. All right. Okay, so we have to be a little bit careful about what I mean by this isomorphism. So specifically, I'd like to show the following. So specifically, we will show that this automorphism group, maybe let me just call this G. I'll just use O for octonions. In fact, over an algebraically closed field, there's only going to be one isomorphism class. And so we're going to show that this is a connected, semi-simple rank 2 linear algebraic group with G2 root system. All right. And here's an outline. There's going to be 3 main steps in understanding this. Okay, so the first is we'll want to show that G is connected. And dimension of G is 14. Okay. This is based on the use of special pairs. Okay. Then we'll construct a rank 2 torus, a maximal torus of rank 2. All right, and then finally, we'll show that G acting on the trace 0 elements is irreducible and faithful. All right, and once we have these three things, it's not so difficult to get our conclusions. All right, so let's begin with part 1. This is going to be based on our study of special pairs. And in particular, we're going to realize the space of special pairs as a homogeneous space, but in 2 different ways. And this is going to get us a lot of the information that we need. All right, so let's go to, no, I want to talk some preliminaries first. All right. Okay, so if we take an automorphism, well, this preserves the trace and the quadratic form. And this follows just by using the characteristic polynomial. And I should really say the uniqueness of the characteristic polynomial. Okay. The next thing that we'll need is some understanding of those automorphisms which fix a particular quaternion subalgebra. So if we take D contained inside of the octonions, a quaternion subalgebra, again, we'll sort of choose some elements. We call this, change that, we'll call this C again. And then realize O as D plus DC, as we saw in the discussion of special pairs. So again, this is just realizing the octonions as a double. If E stabilizes D, then it has to take on a very special form. So maybe I'll call this X. All right, and so what are these things? So X is some element of D, and so is P. So P and X are in D. And the quadratic form of P is 1. So this is essentially coming from Skolem Noether. It has to do a little bit more, plus a little bit. All All right, so if you stabilize a quaternion subalgebra, then you're very close to coming from conjugate, well, almost conjugation. But the main point is that this is a very rigid structure. So once you preserve a quaternion subalgebra, there's not so much room. Okay, and then finally, the last thing I want to mention right now is, okay, so previously we showed that the automorphism group acts transitively on special pairs. One can do the same thing just with an orthogonal group, just because special pairs are only defined in terms of the quadratic space structure. So, so in fact, by Witt's theorem, this implies that SO that the orthogonal group attached to the trace zero elements in the octonion algebra, this acts transitively on the special pairs. And the stabilizer of a special pair. Oh, okay. Let me also say, so this is, we're working over the algebraic closure. So this is really just SO7. Okay. And the stabilizer of a special pair. This is isomorphic to SO. Let me write something a little bit more precise first, and then and this will just be SO5. Okay, so specifically, this is acting on the part which is perpendicular to 1, A, B. So that's going to be 6, 5. Yes, that should be good. All right. Okay, so let me introduce a little bit of notation. So let's let X lambda mu just be the set of special pairs, special lambda mu pairs in O. Okay. We found that this is a homogeneous space, and in fact, we've just realized that in 2 different ways. So on the one hand, this is SO7 mod SO5, okay? And then from this, we can deduce some important things. First off, we can deduce that X lambda mu is connected. And we can also compute its dimension. The dimension of X lambda mu, this will be 11. Okay. All right, on the other hand, we know that this is a homogeneous space for G. Okay, and so what remains to figure out is what's the stabilizer for some special pair. All right, so now we can run through the first step. So we can show now that G is connected, and we can compute its dimension. So let's see. Okay, so let's figure out the stabilizer. And to be specific, so I'm going to take A, B, lambda, mu pair, special pair, special. All right, so we want to look at all of the elements of G which fix AB. Okay, but we know that AB generates a quaternion subalgebra. And this stabilizer of AB is contained in the stabilizer of B. Okay, all right, and based on, I think I called it B above, we know basically from Skolem Noether that these take a very simple form. Okay. So from B, I'll jump back and show you what that is in a moment. Let me just state the conclusion. So from B, we find that this stabilizer of a special pair, G, this is exactly isomorphic to SL2. All right, so let me quickly just jump back so we can see what's going on. Okay, so B was all about what are the automorphisms which stabilize a quaternion subalgebra. Okay, and we found that it has to be of this form. All right, but if we further know that it fixes D, okay, then this is telling us that X is central. X is an invertible element. X is an invertible element in D. Okay. And so X is also going to act trivially on the right-hand side in that second component. And so what's left over, the only thing that we can have are these elements P, and these are elements, invertible elements of the quaternion subalgebra with quadratic form 1. Because we're over the algebraic closure, a quaternion subalgebra is just 2x2 matrices. And if you're an invertible 2x2 matrix, you're in GL, but if you have quadratic form 1, determinant 1, you're in SL. So we find that the stabilizer is just going to be SL2. All right, so we get that the stabilizer is SL2. Okay, and now we get that G is both connected and we get its dimension. So we know that the dimension of G is the dimension of X, lambda mu, plus the dimension of SL2. We found that the dimension of X was 11. We know that the dimension of SL2 is 3, and so we get that the dimension of G is 14. All right, so remember, the main point here is that we were using these special pairs, and we were able to realize this space of special pairs as two different homogeneous spaces, one involving the automorphism group G that we're trying to study, and the other one just involving the special orthogonal group. All right, now we can also see that G is connected. So we saw already from the realization as a symmetric space, as a homogeneous space of special orthogonal groups, that this is connected. And we also know that SL2 is connected. Okay. But since X is G mod SL2, then G is connected as well. All right. Okay, so this wraps up step 1, proving that G is connected and computing its dimension, which is 14. Any questions on step 1?
Why stabilizer of A and B? Why do you want X more? I go back to X and
Yes, that's right. So okay, so X itself is an element of D cross, but given X, that induces an inner automorphism. And the space that we're working with is the space of automorphisms, which of course is just the space of functions. And so even if X is plus or minus 1, the function which it realizes is the identity function. Okay. The P, okay, sorry, maybe I misunderstood. P. So the P which appears in this formula, this doesn't appear via conjugation, but actually just multiplication. Yeah. Okay, I think I'm gonna, because I'm going much slower than I thought. I think what I will do is I'm gonna be somewhat quick about this, about constructing the maximal torus of rank 2. Okay, so one of the important things here is that, let me make a comment at the risk of being even slower. When we're thinking about GLN, for example, a maximal torus is a line decomposition of the underlying space. And something similar is going to happen here as well, except now it's going to be coming from, let me make this maybe like a little bit coarser. To get a maximal torus, we'll first fix some quaternion subalgebra. And if we fix different quaternion subalgebras, we'll get different maximal tori. So the first thing we're going to do is we're going to fix the contained in O quaternion subalgebra. And we're sort of going to construct T relative to D. Okay, and we already know how to write down all of the automorphisms which preserve D, that was from B above. And we're really just going to use this to construct elements of a torus. So we're going to use that same decomposition from before. O is D plus D. Geez, what was I using? C or A? I think I was using C. Okay. So C is orthogonal to D, and the norm is non-zero. Okay. All right, and I just want to define, I'll take lambda and mu, non-zero elements of the field. This is not related to a special pair. This time I'm going to define T lambda mu of D1 plus D2C. I'm going to define this as in the following way. So we're going to have lambda inverse D1. Oh, and I should also mention now, I'm realizing this D as 2 by 2 matrices. So again, sort of using that we're working over the algebraic closure. All right, so I've just defined these. We know that these define automorphisms. These are stabilizing D. Okay, so the claim is that this is essentially the rank 2 torus that we're looking for. This is not quite right. The parameterization is a little bit wrong. I think for the sake of time, maybe let me not elaborate on this too much, but let's just note that T lambda mu, this is the same as T minus lambda minus mu. So you need to reparameterize. I think I'm going to skip this just for the sake of time. Let me just write it. Okay, so let's just set let's set C is going to be lambda times mu, and eta is going to be lambda over mu. And then we can do the following. So this is the reparameterization that we need to sort of correctly realize the maximal torus. So this is going to be, so now I'll take this is an element of K cross squared, and I'm going to send it to the same set of maps, but I just need to do it in sort of a different way, a reparameterized way. So this embeds a rank 2 torus. G. All right. Okay. So we have this rank 2 torus. I want to just make a claim that this is maximal. Okay, I should also, let me just define T to be the set of these T lambdas. It's the same set when you reparameterize or not, just to ease the notation. Okay, right, and then the claim is that this is actually a maximal torus inside of G. Okay, and so the point here is that we, again, because we have this very, very rigid structure of the automorphisms which preserve a quaternion subalgebra, we can actually just compute all of the weight spaces, okay? And then anything which centralizes the torus is going to preserve all of those weight spaces. And then you can just look at the very specific form that we have for these automorphisms. Any automorphism which preserves the weight spaces also, sorry, I'm sort of circling the wrong thing. Let me write it out. It will be more clear. Okay, so let's suppose that we have phi in the centralizer of T, and then phi preserves the weight spaces T. Okay, what are the weight spaces of T? So we have 1 psi times eta and psi inverse times eta inverse, and these are all in D. And we have eta inverse, C inverse, and these are all in D per. Okay? All right, so in particular, phi stabilizes D. So it stabilizes D, and so by part B, it has a very specific form. Okay. All right. Now maybe let me just sort of say you can now just do a direct calculation and show that in fact it is coming from a torus element itself. All right. And so this wraps up part 2. We've constructed a rank 2 torus. We've shown that it's maximal. Oh, geez. Okay. And I forgot, let's see, one minor point that I sort of skipped over. Just quickly. I forgot to emphasize this earlier. We knew that for phi in G, the quadratic form is preserved. And so what this means is that G actually sits inside of S O. Let me just a little bit. I'm going to skirt one issue under the rug. Okay, but anyhow, from this, we get a closed embedding of G inside of a special orthogonal group. All right. Okay, so let's see. right, so now we have part three. So part three is just that G acts faithfully and irreducibly on the trace zero elements. All right, so let's do the easy one first. So G acting on the trace zero elements is faithful. This is essentially by definition. So G are the elements of G, these are just automorphisms of O. And so they fix one. And if they also fix the trace zero elements, then they have to fix everything. So they're the identity. So maybe I won't write any more. G fixes, I'll write it, let's not write it. Let's see. So if G fixes O, trace zero, it fixes all of O because it already fixes one. All right, so faithful is no big deal. The more involved part is that G acts irreducibly on the trace zero elements. Okay, so really what one wants to do here is you first want to prove this for quaternion algebras. This is, you can sort of do this by hand, so I'm going to skip over this step. So the first thing you want to do, you want to prove this for quaternion algebras. This you can sort of do directly. So let's just assume that we've already proved this for quaternion algebras, and let's just see how we can reduce to that when we have a octonion algebra. Okay. Okay. So, okay. So let's take some G invariant subspace. For any quaternion subalgebra, we can consider V intersected with D. So V intersected with D, there are only three possibilities. It's zero. Sorry, let me see. I chose it to be in. Okay, so then there's only two possibilities. So it's either empty, or zero rather, or this is all of the trace zero elements of D. If D prime is another quaternion subalgebra, we know that there exists something in G such that the phi of B is equal to D prime. Okay. We just have to choose special pairs, and then we can map the special pairs to each other. So then the quaternion algebras will go to each other. Okay. All right. So I can apply this phi to the intersection. And this is going to have to be the intersection of V and D prime. Okay. All right. Now, from this observation, we'll be able to produce the irreducibility. Let me just write it out a little bit more formally. So now, let's let V be in V, and let D be a quaternion subalgebra. Containing V. And let's let W be something, some trace zero element. And let D prime be a quaternion subalgebra. Containing W. Okay. Let me make one side remark. Did not mention this earlier. So here's just a fact. This is not so hard to prove, but I don't want to spend any time on it now. Let's see. Yep. So any element of the octonions is contained in some quaternion subalgebra. Okay, so by the above, sorry, let me just say what we're doing again. So we want to show irreducibility, so we're taking something in V and something which is in the trace zero elements. We're just going to map one to the other, assuming that V is non-zero. All right, and so what we know is we have these two quaternion subalgebras. We can find some automorphism which takes D to D prime. And so we get the following. And this V intersect D and so maybe, sorry, I should be just a little bit more precise. So let's let this be a non-zero G invariant subline. All right, so since this is non-zero, when we intersect with D, based on how we've chosen D, the intersection is non-zero. And so this is going to have to be all of the trace zero elements of D by the same fact for quaternion subalgebras. Okay, but we also have that phi of V intersect D. So this is going to be D prime zero. This is V intersect D prime. Okay, so this one is also non-zero, but this contains that arbitrary element W. Okay. So V is all of the trace zero elements. Okay. Okay, any questions on the irreducibility? Oh, I see. Okay. I have two lines. Finish this and then we'll be. Okay, so then let me quickly just wrap everything up. So here's the theorem. Writing has been getting more and more sloppy. Good. So G is isomorphic to G2. Okay. Here's the proof. So we have that G is a linear algebraic group of dimension 14 with a maximal torus of rank 2. Okay, I didn't mention this yet, but the center of G is trivial. Oh, okay. Let's see. So G has a faithful irreducible representation. So it's reductive. Semi-simple because the center is trivial. All right. And so then finally, it's rank 2, it's semi-simple. We can look at all of the rank 2 root systems. We know its dimension is 14, and we can just check that G2 is the only root system that fits the numerics. And we also showed that it was connected, which is important. All right, so sorry for rushing at the end there. Okay, just as a quick recap. So the main tool was this homogeneous space of special pairs. This gave us a handle on this automorphism group. This is also how you investigate F4 as the automorphisms of an exceptional Jordan algebra, different homogeneous space, but it's the same sort of idea to get a handle on these exceptional geometries. All right, thank you for your attention. To avoid a conflict with the next lecturer, that will be all for today. Thanks for your time.